when setting up an infinite number of rectangles as a sigma notation and also as an integral. Today we're going to use sigma notation to evaluate integrals, and I promise you in the future it will get better, but for now this is a little bit tricky, but you will be asked to do it, so please bear with me. We already knew Rule 4 and Rule 5 from the other day. Hopefully you have those memorized. I am adding one new one to your list of formulas you should have memorized. So memorize that one also. These rules we knew. Rule 7 I already gave you, and then rules 8, 9, and 10 were all summed up in that fourth rule I gave you on the sums and sigma notation day. You can pull your constant out front. You can split up your sigmas, whether it's addition or subtraction. So some common sense there. Stuff there. Now, properties of an integral. An integral from A to B, if you need to reverse your endpoints for some reason, which you might have to do because to evaluate an integral you need the smaller value to be on the bottom. To do that, you may switch them, but notice that this negative value shows up. So don't forget, you can flip your endpoints as long as you put a negative. Also, the integral from A to A is equal to 0. Makes sense if you're going from somewhere to the same spot, you're not actually accomplishing any area. When you have just a constant, it's that constant times your upper limit of integration minus your lower limit. And integrals can be split up just like our sigma notation can. Our constants can be pulled out front, and it works over subtraction also. So some rules that are similar to the sigma notation. Now, we need to use the properties of integrals to try to solve this. Bear with me, the algebra is a little bit lengthy, but not too tricky. There is a step or two that you may not have thought of, but this will help us out. So, first thing, I need to write it as a limit.
Teachers, pardon interruption. I just have an announcement here.
From I equals 1 to n, and now we need f of x of I times our change in x. Change in x is going to be our range, 1 minus the 0 over the n, or 1 over n. X of I is going to be our starting value plus our change in x times I, and we need to plug all of these in. F of x of I will be, 4 plus 3 times I over n squared times 1 over n. And now we're going to have to work through some stuff so we can evaluate this notation. Before we can even mess with the limit, we need to do some of the evaluation of our sigma notation. So in our sigma notation, our variable is the I, meaning we can move anything without an I, like this 1 over n, out front. Keep your limit. We're only moving it out front of our sigma notation because it's a constant in terms of the sigma notation, because I is our variable. And we can simplify this a little bit. Now, if we break this up as much as we can, we have the limit as n approaches infinity. Keep your 1 over n. We have the summation from I equals 1 to n of 4 plus 3 over n squared times the summation from I equals 1 to n of I squared. Some of these are easy to evaluate. Keep your limit. Remember, we've not yet touched the limit, so we need to keep it. The summation from I to n of 4 is just 4n, plus 3, keep your 3 over n squared, and our summation for I squared is n times n plus 1 n plus 1 times 2n plus 1 all over 6. So far, so good. Now, this is some algebra that you may not have thought of. And it will work out like this every time as long as you didn't make a mistake. Keep your 4. Now, I'm going to rearrange some stuff. I'm going to rearrange these two pieces. We're multiplied, so that's okay. We get 3 over 6. Have n times n plus 1 times 2n plus 1 all over n cubed. Now, the limit as n approaches infinity of 4 plus 3/6 is 1/2. Watch what I do with this long term at the end. N over n times n plus 1 over n times 2n plus 1 over n. So far, I haven't done anything illegal or wrong. I've just kind of broken up my multiplication. Rather than multiplying together, I'm separating. Now, when we have a single term in the denominator, we can break it up. N over n plus 1 over n. And 2n over n plus 1 over n. So far, if you think about this as multiplication, we're still multiplying. Because right now, those n's in the denominator do not allow us to plug in this infinity that we're trying to deal with. And when we're solving limits, we plug in infinity, or we plug it in first. If that doesn't work, we do some algebra. So we're in the do some algebra step. You notice n over n is 1. This is 1 plus 1 over n. This is, oh, not plus, sorry. 2 plus 1 over n. So, now we're not going to get infinity in the denominator. We can plug that in. 4 plus 1/2 times 1. If we plug in infinity, 1 over n becomes 0. And we end up with 4 plus 1/2 times 1 times 1 times 2, which equals 5. Will they always work out that nicely? Not necessarily, but in this case, it does, and the algebra was long, but not incredibly difficult. Sometimes you'll run into a lucky situation where it is a shape that you know how to find the area of. Let's talk about this one, for instance. The radical 1 minus x squared is half a circle of radius 1. And they want us to find the area, according to this integral, from 0 to 1. Well, how much of a circle is that? A fourth. So our area is going to be 1/4 of a circle, which is pi r squared. R is 1 in this case. So our area is 1/4 pi. So always look at the graph first, or think about the graph as to whether it will be a shape that you'll know how to find the area of. Next one, x minus 1. Well, x minus 1 is a line that looks like this. Crosses at -1 with a slope of 1. And we want the area from 0 to 3. So we're talking this area and this area. Which this point, at 3, when you plug 3 into that, you get the point 32. So really, we have two rectangles. Or triangles, I'm sorry, two triangles. Actually, your area, I think, goes to -1. Now that I'm remembering. So we're actually finding this area. Now keep in mind that this first left triangle is negative area and the right is actually positive area. So the left side is 1/2 base times height, but it's going to be negative because it is below the x-axis. Plus, this next rectangle is 1/2 base times height. So we get -2 plus plus 2, which equals 0. And an area of 0 feels weird, but in terms of an integral and what we're going to be using it for, getting a 0 is not an outlandish idea. So, it is possible. Now you have this last example. I want you to give that one a try, evaluating it like we did our first example back here. Follow my steps, take your time, come with questions to class tomorrow, but I should see a good attempt on your notes if you come in